Hello there. Good evening and welcome everybody, it's Obi-Wan Pez 4 and Simplex Pachenko. We are doing some more math reading tonight, so gather your notebooks, I suppose, and we'll get on with it. Hope y'all are having a good start to your week. Have another treasurer's report to give in the morning. It's fine. This one at least, I just need to go to the bank and then get our statements on everything. Alright, so we were in the Picard-Lindelöf argument on the Banach-Cacciopoli contraction mapping principle. So we were talking a bit about the distance between objects if anybody wants to follow along. We got the arXiv link here. All right. If d sub j is equal to d sub 0, if h sub j, and j is going from 1 on up, then alpha equals 1, and the proof is immediate. Okay, we obviously need to go a little bit further. Map P has unique fixed point x sub infinity in S, moreover for all x and h, and for all n greater than or equal to j, which go from 0 on up. The sequence x sub m is defined by the formula. Let x sub 0 be x. X sub m is going to be the mth composition of the mapping P on X. So, this satisfies the relations d sub j x sub infinity x sub n is less than or equal to c alpha sub m n. Hey Famished, how we doing? Seems to work fine. This time. Catching on more work? Nice. I just got my trivia done. Seems a local coffee shop that I only occasionally went to is now closing. Oops. Looks like they needed my help after all. Psychology, nice. Goodness. Have to write a paper on some subject? Alright, well. Do you have any particular interest? Because if you just have to generically write a paper, that tends to suck. Don't have to worry about it till this week. Yeah. Yeah. Right. D sub j of x sub infinity x sub n is less than or equal to c. Right. In this case, I think that's still a mapping. No, it is actually just a multiplication. All right. Times alpha sub n. What was that? Kappa sub n. Alpha sub n minus 1, kappa sub n minus 1, etc., all the way through alpha sub j plus 1, kappa sub j plus 1, times the distance sub j of x sub 1 plus j and x sub j. Where C is the supremum of the following elements. M is going from 0 to infinity, alpha sub n plus m, kappa sub n plus m, alpha sub m plus m minus 1, kappa sub m plus m minus 1, all the way to alpha sub n plus 1, kappa sub n plus 1. Okay. Series 5 converges by 2. Limit of the supremum of alpha sub j, kappa sub j is less than 1. True crime? Yeah. Okay. In particular, if kappa sub n is equal to L over n, and alpha 1, alpha 2, etc. through alpha are equal to each other, and setting j equal to 0, we obtain that d sub 0 has to be less than or equal to e to the alpha L times L alpha to the n over n factorial d sub 0 of x sub 1 x sub 0. Right. If d sub j equals d sub 0 for all the j's, then alpha equals 1, proof is immediate. Insufficient for Picard-Lindelöf theorem. Shall there exist point x sub infinity from S, the intersection of the spaces h sub j, j is greater than or equal to 0, which is attracting in all metrics. Take x and h denote x sub m. Going to be defined as p m times, or composed m times, on x. Then for n greater than or equal to j, We have estimates d sub j of x sub n minus n plus 1 x sub n is less than or equal to that stuff which is less than or equal to only difference is d sub n of x sub n plus 1 x sub n. That distance must be less than, same multipliers, but also with kappas times d sub j x sub 1 plus j x sub j. First inequality using 1. Second obtained by properties 3 and 4 of operator P. For m greater than or equal to 0, we obtain the estimate that d sub j of x sub n plus m to x sub n is less than or equal to d sub j of x sub n plus m x sub n plus m minus 1. All the way out to d sub j of x sub n plus 1 x sub n, which is less than all of the alpha and kappa stuff. Since the limit of the supremum of alpha sub j, kappa sub j is less than 1, follows that the series given here converges for all n. We set s sub n equal to the following by assumption 2. For large enough n, we have that stuff less than limit of the supremum of alpha sub j, kappa sub j raised to the m plus etc. out to 1 less than infinity. Okay, so it is a finite value. Whence supremum of s sub n is c finite. Therefore, for any j in natural numbers, x sub n is a Cauchy sequence in the metric space h sub j d sub j. And we have x sub n mapped to x sub infinity super j, where x sub n has been mapped by d j times. Is in h sub j. We now check the uniqueness of the fixed point. If z in h0 is such that p of z equals z, then for all j greater than or equal to 0, we have d sub 0 of x sub infinity z is equal to d sub 0 of p mapping x sub infinity to p mapping z. It's going to be less than alphas and kappas from j down to 1, and d is 0, right, by definition, and d sub 0 of x sub infinity and z is equal to 0. Estimate rate of convergence, passing to limits as m goes to infinity. We obtain, hey Kyler, how's it going? D sub j of x sub infinity n sub infinity is less than or equal to c times all of your alphas and kappas from n down to j plus 1. And d sub j of x sub 1 plus j, x sub j. Desired rate of convergence is established lemma 1 proven completely. Whoa. Yeah, we're doing okay, apart from vague hand waving. It's okay. It's just that I don't really understand what I'm doing here, so you know, slightly awkward, but it's fine. Apply lemma to prove the Picard-Lindelöf theorem in Dallas space. R of d dimensions, where d is a natural number with the norm. V norm is equal to the square root of the sum of all v squareds in as many dimensions as we have, right? V sub I. Let t sub 0 be a real number, y sub 0 be a real number of dimension d, a and b are greater than 0. Consider the space-time parallelepiped. Fixed point method proof? Think so. Picard-Lindelöf. R is t and y. T goes from t to t0, less than or equal to some a value, and y is less than some distance b away from y0. Let f be a mapping. Continuous function satisfies the Lipschitz condition in y. Therefore, the distance between f of ty1 and f of ty2 is less than or equal to Lipschitz distance y1 and y2. And absolute value of f of x is less than or equal to m. Let alpha be minimum of a and b over m. As in the classical Picard-Lindelöf argument, the constant alpha gives the length of the interval on which the solution is defined. Introduce the complete metric space H sub 0 in all continuous maps. Y t0 to alpha t0 t0 minus alpha t0 plus alpha. So interval. Mapped onto reals of dimension d, satisfying the assumptions. Y of t minus y sub 0, distance is less than b, and y of t sub 0 is y sub 0 with induced uniform metric. D sub 0 of xy is equal to the max distance between x of t and y of t on said interval of t, going from t0 minus alpha to t0 plus alpha. Introduce Picard operator P. H0 is mapped to H0 by the format. Py of t is equal to y sub 0 plus integral from t0 to t of f of s y of s ds. Suppose y is a fixed point for a Picard operator. By definition, we have y of t0 equals y sub 0. Define the constant. While differentiating 7, the part with the integral up here, yields dy dt is equal to f of t y of t, whence y is the solution of Cauchy problem for equation 8. I might have already read part of this. It's all blurring together. Aye. There exists a unique, continuously differentiable function y super infinity within h sub 0 such that p y super infinity equals y super infinity, and for any continuous function y defines the mapping of distance between t and t0 is less than or equal to alpha, is mapping over to the distance between y and y0 is less than or equal to b. All right, now we're not using Greek letters for that one. Cool. Suppose y is a fixed point for the Picard operator. No, sorry, we're lower than that. Whew. With y of t sub 0 equaling y sub 0, the sequence defined by the formula y super n is equal to p composed n times on y, converges to y super infinity in h sub 0 and satisfies the estimate y super n minus y super infinity. So find the distance between those two objects. Sub c on the interval from t0 minus infinity to t0 plus infinity. No, not infinity. Plus or minus alpha. It's less than or equal to e to the alpha L times alpha L all raised to the nth over n factorial times m. As mentioned above, we cannot simplify our presentation by using the induced matrices d sub j equals d sub 0 on h sub j. Indeed, for the Picard operator, we have thank you so much. Cannot simplify our presentation using the induced matrices. Indeed, for the Picard operator P, we have d of px py is equal to the max on the interval t0 plus or minus alpha distance between the integrals t0 to t of f of s x of s minus f of s y of s ds. Can only obtain convergence in the interval t0 minus alpha to t0 plus alpha with alpha L less than 1 and only with geometric convergence rate. The norm in R super D is chosen for concreteness only. Any other norm can be used instead. The argument works in general Banach spaces. That's pretty awesome. So we don't have to worry about what kind of space you have as long as you have proven that it is Banach space, and in which case you get the yeah, we can get the norm for that. Alright, 3-2, a chain of subspaces for J in the naturals. Let H sub J be the subspace of functions Y in H sub 0, satisfying the equation, supremum on the interval t0 minus alpha to t0 plus alpha. Distance between P, Y of t, and Y of t divided by t minus t0 absolute valued super J is less than infinity. Let C sub J F Y stand for the supremum in 9. Define the metric space D sub J on H sub J by the following formula. D sub J of x, y is equal to supremum on the interval as long as t is not t0 itself. Okay, fair. X of t minus y of t over t minus t0 to the j. Check that the supremum in 10 is finite. Define the following linear bounded operator kappa on Banach space, C on the interval from t0 minus alpha to t0 plus alpha. For G in C, it's easy to verify that for N in the naturals, we have following. And something really big. Alright, we write RL G of t is equal to G of t plus L times the integral from t0 to t, G of s times e to the L absolute value t minus s By definition, the operator RL is monotone in the following sense. G of t is less than h of t for all t. For all t in said interval, it implies that r sub l times g is less than or equal to r sub l times h. Hey, Megalomorph. Maybe. We're on page 5. This one. This was proofs of existence and uniqueness of ordinary differential equations, but from different perspectives. So I am trying not to make it feel like I'm having a bat swatted across my face a bunch of times, so. Okay. All of that. Okay. Finally arrived at the desired estimate. D sub j of xy is less than c sub j of fx plus c sub j of fy, all multiplied by 1 plus L. That's not composed, though. That's just super j times e to the L alpha minus 1. By definition of metrics, d sub j satisfying the inequality given here. Okay. One way of checking completeness of the space H sub j is to take y0, y1, y2 to set u10 of t equal to y1 of t minus y0 of t over t minus t0 raised to the j. U of 20 of t is going to be y of 2 of t minus y0 of t all over t minus t0 all raised to the j. Note that by definition we have u10, u20, and that d sub j of y1, y2 is equal to the maximum when the distance of t from t0 is less than alpha of the u10 and u20. Completeness by Chebyshev metric now implies completeness of metric d sub j can also proceed as follows. Check metric spaces are complete. Consider a Cauchy sequence x sub n. Inequality given here implies there exists a function x within C on the interval t0 minus alpha to t0 plus alpha such that d0 of x sub n x is mapped to 0 from the inequality d sub j greater than or equal to this primum. So when mapping P, we can instead map still x sub m n to x sub m. And we get a constant multiple of alpha L out front. Sequence of real numbers C sub j of f x sub n is Cauchy's sequence. We let C be its limit. Limit as n goes to infinity of C sub j of f x sub n is C, which is finite. Taking n to infinity, the inequality here, distance between P x sub n of t and x sub n of t is less than or equal to C sub j of f x sub n times t minus t0 to the j. We obtain that P x of t minus x of t is less than or equal to c times t minus t0 raised to the j. Therefore, x is in h sub j, and the metric space h sub j is complete. My goodness. I was kind of hoping it would be a little more accessible. Same argument works in complex time. Endow the space C super D, where D is a whole number, with the norm given as the max of phi sub j. Let t0 be c, z0 be c dth dimension, a be greater than 0. Consider the complex space-time parallelepiped. We already did that in the previous one, so same deal. Be a holomorphic function satisfying Lipschitz condition. Again, same thing, but now it's in real and non-real. All right, norm distance between the two f values is going to be less than or equal to L times the norm value between the two z values for any t and z1, z2 in the R space that was defined above. Introduce metric space H0 of all holomorphic in U, continuous in U bar. Okay. Z is going to be the mapping from U bar to V bar, which satisfies the assumptions that Z of t minus Z0 is less than or equal to B, and Z of T0 is equal to Z0. space H0 is endowed with uniform metric D0 of ZW is equal to the max as where T is within U bar. Z of T minus WT normed. Introduce Picard operator P, given there. Picard-Lindelöf theorem in complex time. There exists a unique holomorphic function Z super infinity maps U onto V such that P Z infinity is equal to Z infinity for any holomorphic function Z mapping U to V with Z of T0 equal to Z0 sequence defined by the formula Z to the N is equal to P composed. Doesn't actually say anything there. It should be N, I think. Z uniformly converges to Z infinity and satisfies our estimate here. Norm distance between Z super N and Z super infinity on the space U bar is less than or equal to e to the alpha L times alpha L raised to the N over N factorial times M. Proof existence uniqueness theorem in complex time based on contraction mapping principle can be found in instance in 25. Cool. Chain of subspaces. Consider metric space H0, D0. Recalling that in the Weierstrass theorem, the limit of a uniformly convergent sequence of holomorphic functions is a self-holomorphic. See that H0, D0 is complete. C sub j on or of Fz stand for supremum. Oy. Woo! Okay. Define metric d sub j on h sub j by the formula d sub j of zw is equal to the supremum on u bar, t on u bar, and t is not t0. Take the norm of z of t minus wt over t minus t0, all raised to the j. Check that the supremum 14 is finite for all values. Define the linear bounded operator kappa on Banach space for real continuous functions g in C of u bar by the formula given here with the integral. Again, integration takes place over internal joining t and t0. For n in the naturals, we have the following. And more messy stuff. By definition, R sub L is monotone with the following sense. Cool stuff. Definition of Picard operator. Therefore, the following is true. Metric d sub j is thus well defined. By definition of metrics, d sub j satisfy the inequality d sub j better of ZW is equal to supremum where t is on u bar and not equal to t0. That, right, same one we just had, less than or equal to supremum as t is on u bar and not t0. It's the exact same thing but multiplied by the absolute value of t minus t0. As we're getting, yeah, we're multiplying both top and bottom by that, t minus t0. That's fair enough. Must be less than or equal to. So we've taken an absolute value of t minus t0, and we've moved it inside of the norm. I don't think I like that very much. Less than or equal to alpha d sub j plus 1 of zw for all z and w in h of j plus 1. Completeness. Take y0, y1, y2 in h sub j to set the following. We already did that up above. We have u sub 10, u sub 20, c of u bar, completeness of Chebyshev metric now implies completeness of metric d sub j. One can also proceed as follows. We check that the metric spaces are complete. Indeed, consider a Cauchy sequence z sub n, inequality d sub 0 of z sub n z sub m is less than or equal to alpha super j times d sub j of z sub n z sub m is mapped to 0. Implies there exists a function z in c of u bar, on u bar, such that z is holomorphic in restriction to u, and such that from the inequality d sub j of z sub n z sub m is greater than or equal to the supremum where t is on u bar and not t0. Difference between the norms of all of those things. Allows us to obtain the below. Similarly, for all this stuff, therefore the sequence c sub j of f z sub n is a Cauchy sequence of real numbers. Set c equal to limit as n goes to infinity of c sub j of f z sub n is finite. Taking n going to infinity in the inequality given here, we obtain that p z of t minus z of t normed is less than or equal to c on t minus t0 raised to the j. Therefore, z is in h sub j metric space. H sub j must be complete. Okay. Nested images. Picard operator P maps h sub j onto h sub j plus 1. Because for all z in h sub j, we have the following. P of pz minus pz. Okay, so yeah, this is nesting the previous one. So it's going to take the previous argument, and we're just doing another nesting of p on pz minus z. Argument follows as already has. So okay, rate of convergence. In order to apply lemma 1, it remains to prove that the assumptions 2 and 4 hold. We have d sub j plus 1 of pz pw is equal to the supremum, where t is on u bar but not t0. 1 over t minus t0 raised to the j plus 1 times the norm of the integral of, as we go from t0 to t on f of s z sub s minus f of s w of s ds, which is less than or equal to the supremum argument. Right, so instead of the norm on the outside, it's now a norm on the inside. L times z of s minus w of s, which is less than or equal to the definition of z? No, that's not true. What is that? There are definitions above. I'm missing some stuff. Just me, personally. Something's sticking out of my feet. In particular, we have kappa sub j is equal to L over j going to 0. So set z super n equal to the nth composition of p on z. Using lemma 1, we obtain that z super n on the d0 mapping to z infinity. Since z infinity is within the intersection of all h sub j, follows that z super infinity of t is equal to p z super infinity of t is equal to z0 plus integral from t0 to t of f of z s z super infinity of s ds, and obtain desired rate. D sub 0 of z super n z super infinity is less than or equal to e to the alpha L times parentheses alpha L of raised to the nth power over n factorial times m. Okay. Gottfried Wilhelm Leibniz proposed the term differential equation, equatio differentialis, and Leonhard Euler in St. Petersburg obtained the first existence theorems 9, using, in modern terms, the method of approximating the solution by a convergent sequence of piecewise linear functions, the method that bears Euler's name today. Vyacheslav Alexandrovich Dobrovolsky describes the history of the existence and uniqueness theorem for ordinary differential equations in the 19th century. Dobrovolsky conjectures that Augustin Louis Cauchy may have been aware of the existence and uniqueness theorem already by 1820. In 1844, the abbot François-Marie Napoleon Moignot published a course in integral calculus based on Cauchy's letters and included a proof of existence using Euler's method. Lessons 26-27. Moignot gives the sufficient condition that the partial derivative of f with respect to y be continuous and bounded for existence of solutions of the ordinary differential equation when written in the form dy is equal to f of xy dx. Uniqueness of solutions is very briefly mentioned. The extension to a system of ordinary differential equation is treated by Moignot in lesson 39. Again, the uniqueness of solutions is treated very briefly. Existence and uniqueness under Lipschitz condition is due to Rudolf Lipschitz, who again uses the Euler method and cites neither Cauchy nor Moignot. Lipschitz gives a detailed proof for both the existence and uniqueness of solutions and makes the remark that uniqueness need not hold if the Lipschitz condition is not verified, without, however, providing specific counterexamples. Helpful. As we now proceed to a brief review of iteration proofs of existence and uniqueness theorem, let us recall first that solving equations by iterating a contraction is a procedure with counterparts in antiquity. Heron of Alexandria in his Metrica uses in modern terms the contraction x goes to 1/2 times the quantity x plus r over x in order to find the approximate value for the square root of r. A very precise approximation on root 2 on the tablet, YBC 7289, paleographically dated to the first third of the second millennium BC, and currently owned by Yale Babylonian Collection, YBC, has led scholars to the conjecture that the scheme was already in use during Old Babylonian period. That's pretty bonkers. Much longer historical remarks section than you were expecting. Yeah, I was expecting that one page, that couple of paragraphs was going to be it. I was going to go to the next page and it's like remarks or acknowledgments or whatever. Just to let everybody know, ads are going to start in about 30 seconds, so we'll get that going and everybody can take a break, stand up, walk around, because goodness knows you probably listened to me prattle on long enough already. And then we can also look at the approximate value of the square root of r using this formula, because I think that that's one of those things that was like has been taught throughout centuries, and like my generation kind of lost out on because we were just like, yeah, do the calculator, just hit the square root button, and didn't necessarily go through and like try it out, even in calculus. We did Newton's method. That was different. Anyway, see you in 3 minutes. Thank you for coming. It's Zach, everybody. Welcome on in. How's things going? Just getting back from break. My spouse is doing a show for a local professional theater group. I guess the theater hall is like the big professional theater in town, but her group is a good mix of people who are just wanting to do theater for theater's sake. And so she just got back from tech rehearsal, which I said, "How'd that go?" She goes, "It's about as well as you'd expect tech rehearsal to go." Great. All week her mantra has been, "Tech is the worst." Hey, Waffle Lover, how's it going? Alright, so we're gonna do some Tai Chi as usual. We are down to small single digits in terms of the number of streams that we're gonna have in this space, with all of my kids' stuff laying around in here. Unfortunately, it will be a bit of a smaller space, I've realized, for the new place, but we'll make sure that we have enough room to at least do some more Tai Chi, and even if it is basically even physically restricted, similar to what we've got here with this basic physical restriction of just stuff. It'll be much more realistic and like actually physically restricting, because it's possible I could just smack into a wall. It'll be fine. It'll be fine. I can't steal one of the giant bedrooms or something like that for it, unfortunately. It'd be really awesome. The kids are getting like 20 by 20. Not quite, but more like 15 by 15. It is big. Spouse and I are taking the place up in the roof again, essentially, and so it's gonna have we're gonna have the eaves coming down on either side, which is going to be terribly interesting, because that means that like all of our wardrobes and stuff have to be in the middle of the room, otherwise they're not gonna make it. So we have one central wall where we might be able to put a single wardrobe, and the rest of them, if we want to put them against like the walls, they have to be about no bigger than that. So 3.5 feet. Great. So, as usual, we just do a bit of warm-up here. Make sure that the synovial fluid is moving through your joints. A little bit of blood flow helps out everything, especially when doing a number of martial arts. This can actually, you can pretty seriously hurt yourself if you do some of the more whippy type stuff, because your capillaries will end up having extreme pressure put on them. Can increase your can increase the local blood pressure in your fingers to dangerous levels, so like over 200 systolic. Not great for your blood vessels, but if it's done for short enough periods of time, then it's fine. Yeah, I know, 15 feet. 3 meters by 3 meters, give or take. Whoa, no, 5 meters. Wow. 5 meters by 5 meters, roughly. So, yeah. I mean, like, probably roughly the size of this room, give or take. Kids can have all their own stuff in their own rooms, and then I don't have to deal with it. All of this stuff, also, all of our board games are going to be able to go into their separate second living room. I think we have a lounge. Have, like, you know, one with a fireplace and a TV, and a whole separate room that we're going to be able to, like, take our TV that is currently downstairs and just hook up the video games to it. So we don't have to deal with it. Sharing. Psh. Alright. Tai Chi. Tuck into the inguinal crease, which is that nice little spot between your thigh and your abdomen. And then when we do that, we come out to the side, straighten everything out. Relax a bit. Tuck left and energy ball. Turn on the heel. Move forward. Step left. Ward off left. Keep the right hand down here. And then from here, we turn on the toes of the right foot, which is like the exact opposite of what I've been doing. And then step. And as we shift the weight, we go to a ward off right. Tuck in on the left heel. Roll back. Press and push. From here, turn on the right heel. To this sort of like slightly awkward pigeon-toed stance. We come around this way, come down and tuck and duck a little bit, and it allows us to come back with a single whip, step out and wait, shift the weight, turn the hand, turn the foot. You can't really see the feet. That's all right. Come in, back up, and this is lift hands. Everything comes back, and we do a shoulder. And then from here, I'm going to turn so that everybody can actually see this. We do the shoulder here, and then we come up and do white crane. From here, going to do brush knee. So we circle our hands around to do blocks. Step in, and all of this weight comes forward in the hands, here to block, here to strike at the same time. And then we step up sideways, do strum the lute, and then from here we do another brush knee. Okay, from brush knee, we then rock the weight back, turn on the heel to 45 degrees, rock forward, and bring this into a fist. We're then going to come through with the right foot, stepping up, and whip the fist around, block with the left hand, we're stepping sideways with the right foot, step through with the left foot, and give it a punch. From here, we tuck into the left inguinal crease, come back around to the bottom of the elbow with the left hand. We're going to, essentially what's happening right now is we've got some sort of weight of another person's arm that like we're blocking. And so here what we're going to do is shift the left hand in to take the weight, slip the right hand out, and then push. And once we do that, we then lean back and turn pigeon-toed again. And then shift weight left, pop the arms around, move the legs to more of a, I call it Kima stance, because that's what I learned in karate, but it's like a horse stance, where you're essentially like standing astride. And then from here, your hands come up. The right hand is going to hold up, essentially the left hand. We're going to be leaning ever so slightly on the left as well. Then, from here, this is the part that I'm still learning. We pop this down with our hands, turn on the right toes. Left hand comes up, right hand stays low. We step backward into what I would call a fugal stance, where the right leg is facing a 45-degree angle away from where, well, 135-degree angle away from where our front leg currently is pointing. And then we're going to shift. Then we're going to shift our weight and turn the left foot so that it's heading more or less in the, well, more or less to the 90 degree from where it is now. When we do that, this is called carry tiger to mountain. These have very whimsical names, but reason being that somebody who is like attacking very aggressively and hard and like lots of fists and lots of muscles is typically known in Tai Chi and similar martial arts as like tiger. So basically at this point, what we're doing is we're like blocking something that they're doing and then basically just grabbing them and moving them off like this. So move the weight off, and it basically is just grabbing them and then throwing them that way. All right, and then from here we bring the right arm up. We do a roll back, press, and push. And again, come back to here. We're going to do another one here and snap out. Left leg to a 45-degree angle. And now we're in, right, single whip again. We step back out this way, lean forward, and again, in this block. Then, right. So we're facing toward the corner of the room. And then in order to straighten ourselves back to the side of the room, we're going to do a double whip. So here we bring both of our hands back, lean back, right? We lean back, pop up the front foot, and then whip around. The right foot is moving forward. Ooh, where are we going with this? I think this one, our right foot steps forward. We basically slapped somebody here and like let our hand either guide something that's coming at us or use it as counterweight, come through, And then when we take a step, we're going to do another punch here. And this is a fist underneath. And that is about as much as I remember. Pretty sure I learned a few moves after this, but we're going to have to pick it back up on Wednesday. We'll probably do another good form on Wednesday so we can remind ourselves what it's supposed to be. Yeah, sorry, Zach, I didn't catch that message. We're moving on the 23rd, 24th to a new place. It is going to be fabulous because I'm going to have my own streaming space and I don't have to share it. As fun as this is, we get to have our own. Yeah, we get to have our own spaces and do cool stuff without needing to get in each other's way all the time. I don't keep having to nag the kids to clean up the space that I'm streaming from. That I won't feel bad because they don't do it anyway. Isn't it just? Okay. So, coming back here, right. We wanted to look at how to do the approximate value of the square root of r. So, if we were to what's the citation for this paper? Like this whole paper is at this DOI? No, sorry, arXiv, not DOI. If you mean the stuff for 13, that would be number 16. Reference 16, D. Fowler, Historia Mathematica, 1998. And Russian. Not helpful. Unless, of course, you know Russian, but, I do not. Okay. X to 1/2 x plus r over x. Okay, so limit as it approaches infinity of this scheme is going to be equal to square root of r. So, if we say, let's just plug in x equals 1, r equals 2 for the initial stuff, we do 1/2 1 plus 2 over 1. Ooh, that's going to be a terrible mistake. Right, go to x, which is going to be, in this case, 1/2. This is going to be 3. So, okay, that's maybe not awful. 1/2, 3/2 plus 2 over 3/2. That's That's going to be 1/2 times 3/2 plus 4/3, which is going to be 8/6 and 9/6 is 17/6. Oh, this is going to get ugly. 17/12. 1/2 17/12 plus 2/17/12. And we're just going to automate this eventually, but you know. 12 and 17 is going to be 14. 7 and 2 make 9, 10. And oops. And then 1 and 1 make 1. That makes 2. All right, 204. Uh, 17 squared is going to be 149 and 2 times 70. So 140 to 89. Cool. Plus 24 times 12 is going to be 144 times 2 is 288. Over 204. Okay, 577 over 408. Just out of curiosity, right? Of course, it's not curiosity. We want to know what this is. Saves his bookmark for later. Yeah, the whole point was existence and uniqueness of DEs, and then somewhere along the way it lost me because it was trying to talk about all sorts of other stuff that I'm like, that's not really in my wheelhouse. It's not my part of DE, really. 577 over 208 is 2.774. That is not a very good approximation for the square root of 2. Oh, 408, jeez. 1.414, much better approximation for the square root of 2. All right, square root of 2 is 1.414. 21, match, differ. Our example is 5686. The actual value is 3562. So if we were to take the above 2, oops, and do percentage, right, over actual, is about a 1.5 times 10 to the negative 4th percent. So, yeah, it's pretty good. And that was just the, 2 iterations that I could do by hand, starting from x equals 1. Similarly, if we just wanted to do this with literally any other number, if we want the, right, x equals, again, let's just do x equals 1, r equals 19. Right, this is going to get ugly. This is going to be 1/2 times 1 plus 19 over 1. It's going to get 20. Half is going to be 10. Very poor estimate for this particular square root, but naturally, we're going to say this is going to be 1/2 10 plus 19 over 10. It's going to be 11.9 over 2. So that's going to be a 5 point, and already we're incredibly better. 11.9 divided by 2 is going to be 5.95, right? Or I guess we could keep it as, you know, fractions. Okay, so that's going to be out of 20. It's 119. Yeah. Obviously. Come on, Obi. 1/2 times 119 over 20 plus 19 over 119 out of 20. This is going to be so gross. 119 out of 20, that's not too bad, but it's going to be 238, 0. 4760. Okay. 119 squared is going to be 100 plus 10 plus 9 plus 2 10 by 100s is going to be 1,000 plus 2 10 by 9s plus 2 9 by 100s. Just in case anybody doesn't remember where this all comes from, this is my channel name after all. This is a three-dimensional simplex. 100 plus 10 plus 9 raised to the second power. We're looking at a three-dimensional a plus b plus c simplex that then we want to know where all of these things go. These are the standard numbers that fill in the Pascal triangle. So we got 1, 1, 1, 1, 2, 1, and then it's like that on every face. So around this thing, it's a 2 and a 1 and a 2 and a 1. And this one's also a 1 there. So on row 2, this is what happens when we square a 3-digit number. We're going to treat it like a three-dimensional simplex, come down to row n equals 2, and then we can fill in with all the different combinations using 1s and 2s for all of the coefficients. That's it. So this is going to be 10,000, 12,000, 13,008, 13,980, 14,080, 14,161. Hope that's right. Be terribly embarrassing otherwise. 14,161. Woo! Okay, so my mental math didn't fail me. That's the good news. Yet. Okay. So that is this one right here. Oops. That's going to be 14,161 over 4760 plus 380. Okay, so this 20 has to be multiplied top and bottom, and then we also need another 20 top and bottom to fill out the denominator to make sure that we get equal denominators. So this is going to be a 20 squared on top is 400 times 19. So 36, and 4 makes 7, and then double 0. So 7,600. Over 4760 is going to make a 21,761 out of 4,760. Okay, and then we check. So 21,761 divided by 4,760 is going to be 4.5716, which sounds reasonable for, as much work as we did here. Square root of 19 is 4.3588989. So, okay. It's, it wasn't great, but here's the thing, right? If we had started with a value that was much closer to the actual correct value, right, this is going to be something that's going to be a pretty heavy influence. So if we do like x equals, I don't know what it is, let's say it's just 4. We already know that it should be, more than 4 and less than 5 because it's between 16 and 25. If we're just doing a naive guess, right? Guess x equals 4. Then we want here a 1/2 4 plus 19 over 4. Much better guess. Right? So then this is going to be 4. We need a 16, and a 19 is going to be a 35 over 8. A 1/2 times 35 over 8 plus 19 over 35/8. So again, we're going to multiply these out. We need to multiply the numerator and denominator of our second number by 64. 1 to get rid of the compound fraction to move the 8 to the top. The second to put another 8 in the denominator so that we have equal exponents. No, not exponents. Equal denominators. Again, we're going to have to then multiply the first fraction top and bottom by 35 for, again, much the same reason. So 35 squared is going to get us a 925, and 15 makes 150 times 2 is 300. So a 1225. So this is going to be 1225 over 16 plus 19 by 64 is going to be a 36. This is going to be a 4 plus 54 is 58, plus 3 is 61. And then 10s are going to be 1 times 6 is 6, plus 6 is 12. So 1216. Over, here is a, oops, that is not 16 in the first one. That is 8 times 35 times 2. So 8 times 70 is going to be a 560. Okay, which is going to be a 2441 over 560. That looks pretty good as it sits. 2441 over 560 is equal to 4.3589. So it is equivalent to three decimal places, 4.358. And then here we differ by the actual is 89, and our current value is a 92. So 3 tenths, hundredths, thousandth, 10,000th, right? 3 100,000ths of a value for the absolute difference. And then if we want percentage difference again, do that one minus that one, parentheses, divided by actual, is again, well, in this case, times 10 to the negative fourth percent. So again, it's such a small difference that, like, this would be a reasonable number to use if you just want, like, 2 or 3 significant figures. Close enough. In this day and age, sure, we do actually want more accurate values, and so we will be a little bit more demanding in terms of the like the precision that we want, but generally speaking, right, if you're just trying to get a value for square root of 19, 2441 over 560 is pretty good. Is a reasonable approximation. Square root 19 approximate. And again, if we just take this and say, hey, just repeat it for me and throw it in the calculator or something, it will come up with a value that is much more accurate. I mean, literally will make it to as many decimal places as you want it to go. You just basically recall, your stored value for the square root of 2 and say, is it this? And if it says, yes, it's that, then say, fine, just exit the program. Because it doesn't keep as many decimal places as it like can possibly store. I don't know actually how many decimal places one of those would store. So if you just said, are the numbers equal? In theory, it'll never be equal, but at the same time, I don't know how many decimal places it stores. So it is possible that it could stop it after 9, 10, 15 decimal places and be like, yep, got it. Okay. For solutions of ordinary differential equations, an iterative scheme foreshadowing the Picard method already appears. Dobrovolsky indicates in the paper 17 by Joseph Louisville, one of the first contributions to what became later known as the Sturm-Liouville theory, misprint there. Émile Picard first introduced the iterative method that now bears his name in the study of partial differential equations. So here we have the second partial derivative of u with respect to x, second partial derivative of u with respect to y, plus a times the partial derivative of u with respect to x, plus b times the partial derivative of u with respect to x, that should be y also, plus cu is equal to 0. Picard applied the method to the study of ordinary differential equations in a subsequent paper. Lindelöf gives the proof essentially in modern form, together with the estimate O of alpha to the n over n factorial for the rate of convergence. Note, however, Lindelöf includes proof of uniqueness of solutions by contradiction with the Lipschitz condition, and does not seem to include in his analysis the observation that the Picard iteration scheme does by itself furnish both existence and uniqueness proofs. We now proceed to brief review of topological proofs of existence and uniqueness. Particular case of what became known as the Brouwer fixed point theorem was obtained by Piers Gregorovich Bohl in 1904. Results of Bohl are specifically geared toward applications to ordinary differential equations. Können dazu dienen, periodische Lösungen von Differentialgleichungen nachzuweisen. Oi. See brief discussion by Mishkis Rabinovich in 20. Let us turn to 20th century developments in Lvov following the account of R. Duda. Stefan Banach established the contraction mapping principle in 1920 PhD thesis, published in 22. Contradiction mapping principle is formulated by Banach for self-maps of complete normed vectored spaces. The spaces are called Banach spaces today, and that are precisely introduced in Banach's thesis. Stefan Banach did not discuss possible applications of the principle to ordinary differential equations. A few years later, however, the idea of proving the existence of solutions for differential equations using topological considerations based on Brouwer fixed point theorem started to flourish in the Lvov school. Julius Schauder, building on previous work of Birkhoff and Kellogg, proved his famous fixed point theorem precisely with a view towards solving differential equations. Let us emphasize that the topological methods of Schauder only give existence of solutions, not uniqueness, much less a procedure for finding approximate solutions. In the USSR, the investigations of Schauder were pursued by A.N. Tikhonov, who again only considered the existence. Formulation of contraction mapping principle for general mapping spaces and its application to the proof of existence uniqueness is due to Renato Cacciopoli. Cacciopoli is the tragic hero of 20th century Italian mathematics. Cacciopoli made a determining contribution to the development of the Italian school of analysis. In the words of Alessandro Figa Talamanca, Cacciopoli's ideas ebbero un'influenza decisiva sullo sviluppo dell'analisi matematica in Italia. Si può dire che un'intera generazione di all'inizio ha attinto da lui nuove idee, indirizzi e ispirazioni in un periodo in cui l'Italia si era isolata culturalmente dal resto del mondo. Si deve pertanto a lui se nel dopoguerra l'analisi matematica in Italia ha potuto reinserirsi nelle grandi correnti del pensiero matematico mondiale. 5. Okay. 4. Encyclopedia Italiana, 2004. Had a decisive influence on the development of mathematical analysis in Italy. It can be said that an entire generation of analysts obtained from him their new ideas, direction, and inspiration in a period in which Italy had culturally isolated itself from the rest of the world. It is therefore due to him that in the post-war world, post-war period, mathematical analysis in Italy was able to reinsert itself in the great currents of the world mathematical thought. Well. I don't know Italian, by the way. So, those of you who speak Italian, I'm sure that was painfully obvious. To everybody else, it may not actually have been. We will have to just real quick take a look at this because this is hang on one sec. Very, very pertinent. Anybody who doesn't know Kids in the Hall. I'm going to have to steal that clip sometime. Use it. It is a great clip, by the way, if you know Dave Foley. He was part of a sketch comedy group called Kids in the Hall in 1990s. And it was all Canadian comedians. And they did a whole bunch of seasons of their show. They recently came out with a new series where it was, them as old men coming back to the world of comedy. It was very well received. They're still funny as ever, so I can highly recommend that. If you have, I want to say it was on Amazon Video, but the years between unification of Italy and the First World War are often defined as the golden age of Italian mathematics. The buoyant spirit of this optimistic period can be seen from the famous words of Eugenio Beltrami to Ernesto Cesaro, in which I imagine that that's Ernesto Cesaro of the Cesaro summability. in which the Lombard mathematician, himself son and miniaturist and grandson of a gem engraver, complements the book of his Parthenopean colleague for davvero il requisito dell'italianità, vale a dire di quel quid ci risulta dal connubio della serietà collegialità della parola e del pensiero, cioè dell'elaborazione artistica del materiale scientifico. Really the requirement of Italianness, that is to say, that quid that results from the union of seriousness with the agility of speech and thought that is of the artistic elaboration of scientific material. Words that Vito Volterra describes as sober, efficient, and precise characterization of la produzione matematica italiana non solo recente ma di tutti I tempi. Italian mathematical production not only recent but of all time. An avid reader with deep interest for Proust and a special affinity for Rimbaud, whose portrait, together with that of Galois, he kept on his working table, an organizer in Naples of a cinema club devoted to contemporary film, a talented pianist who had contemplated a professional performing career, would Cacciopoli have recognized himself in Beltrami's words. Ennio de Giorgi says, per quanto sia difficile e incauto entrare nel mistero di un uomo, se dovessi vedere un filo tra l'interesse artistico, l'interesse scientifico, l'interesse sociale e civile di Cacciopoli, lo vedrei in questa aspirazione di fondo all'armonia e nel dolore c'è tutte le varie disarmonie ai vari livelli gli procuravano, and develops perché se in lui l'idea dell'armonia pitagorica. You're chopping out a lot of words here. C'è la costruzione matematica deve essere bella e armonica, non può essere priva del bellezza. As difficult and imprudent as it is to try and enter into the mystery of man, if I were to look for a thread joining the artistic interest, scientific interest, and social and civil interest of Cacciopoli, I would see it in his profound yearning for harmony, and in the pain that all various disharmonies at various levels gave him, because in him there is the idea, the Pythagorean harmony, that mathematical construction must be beautiful and harmonious, and it cannot be devoid of beauty. I mean, it's very nice sentiments. Okay, we're going to take a break. We're going to get a 3-minute ad break, and then we will be back for the last section of this historical context that we're going to get here. So thank you so much, everybody, for coming. Anybody who doesn't know me, I'm Obi-Wan Pez. This is N Simplex Pachinko. We do mathy type stuff here on Mondays and Wednesdays, and we do gamey type stuff the rest of the time. So see you in 3. We return. All right. We'll do this one just because I hate it. And 1, 2, 3. Highly recommended for everybody else to do these exercises too, you know. Okay. Okay. Renato Cacciopoli was born in Naples, 20th of January 1904, into the family of Surgeon Giuseppe Cacciopoli, private physician to Queen Margherita Sofia Bakunina, the daughter of Mikhail Androvich Bakunin. Cacciopoli left a profound impression. Several surveys, in particular those published on his centenary in 2004, are devoted to Cacciopoli's mathematics. 5 biographies, as well as the film Morte di un matematico Napoletano, 1992, directed by Mario Martone, loosely based on the events of his life, present Cacciopoli's person to the general public. In these brief remarks, we follow the survey by Carlo Sbordone and the biography by Lorenza Foscini. On obtaining Maturita Classica, Cacciopoli entered the University of Naples to study engineering, but then switched to mathematics. In the last years of the 19th century, Nicola Trudi, Gabriele Torelli, whose son Ruggiero proved what is today called the Torelli Theorem, and Ernesto Cesaro, Alfredo Capelli, all worked at the University of Naples. During Cacciopoli's years as a student, Pasquale del Pezzo, Duke of Cajanello, held the chair of projective geometry at the university, whose rector he had been from 1919 to 1921. Of decisive impact on Cacciopoli was the arrival to Naples of Mauro Boccone, whose assistant Cacciopoli became. His active public stance made his life in fascist Italy difficult and dangerous. Yay. In 1938, in order to avert a disaster, the family had to place him into a psychiatric asylum. His piano was brought to him so that he could continue to practice. Cacciopoli's meeting with André Gide in Sorrento in 1937, meeting that Gide in December 1945 journal entry described as unforgettable, gave rise to a report by the secret police. Italian. A regime which rests only on the personal fortune of a man can only be a transitional regime. couldn't possibly be relevant. The fascist regime collapsed, but in post-war democratic Christian Italy, Cacciopoli remained suspect, unable, in particular, to travel abroad. With sneering brutality, his exit visas, while granted on paper, were issued in such a manner as to render actual travel impossible. As just one example, Cacciopoli was even prevented from going to Amsterdam in 1954. Facing the abyss of humiliation proved unbearable. In his own words, Naples is a swamp, and we are the sick fauna of this swamp. Cravenness makes us fat and kills us at the same time. He then took his life on 8th of May, 1959. Jeez. His work on elliptic equations developed to a degree in rivalry with that of Petrovsky, but we are not aware of any direct contacts between the two, or any of the mathematicians in Moscow school. Nonetheless, a few years after the appearance, during his feverishly productive period, of the 1930 note on existence and uniqueness of solutions to differential equations, his work was included in the 1939 textbook based on the author's 1936 Saratov lectures by Ivan Grigorovich Petrovsky. Cacciopoli in his Levi Civita family home. We are deeply grateful to the heirs of Tullio Levi Civita for the kind permission of the use of the photograph. Supported by Russian Science Foundation, or grant number, whatever. Okay. All right. Tonight is hashtag not sponsored by Seven Brothers Buzz Honeycomb Beer. It is quite sweet, which one would expect from a beer that says honeycomb on the side of it. All right, when mathematics meets painting, Fibonacci geometry, Cubism, and visual abstraction. Sankhadip Mondal, R.N. Mohapatra, Department of Mathematics, University of Central Florida. This paper explores the Fibonacci sequence and the golden ratio as organizing principles for visual composition and abstraction in painting. The author shows how recursive proportional systems, long associated with natural growth and aesthetic harmony, inform artistic structure and visual balance. The discussion traces Fibonacci-based geometry from Renaissance art to modern and contemporary practices, with particular attention to Cubism, where fragmentation and multiple viewpoints echo principles of recursion and geometric division. Those selected artistic examples and mathematical insight Through selected artistic examples and mathematical insight, the paper demonstrates that Fibonacci geometry functions not merely as a symbolic reference, but also as a generative framework shaping visual abstraction and artistic expression. Now, I do have to put a little footnote on that, that there are many pieces of art, both on canvas and in real life, that people have said long have attributed to the golden ratio, to Fibonacci numbers, and it oftentimes is just not true. The Parthenon, for example, is one example that has been like subject of misinformation because people say, like, if you check it, it's like the golden ratio, and if you look at it's not even close. It's like a 4-to-1. The width versus the height of the top triangle portion just is not even remotely close. Some of the other measurements might be sort of close if you squint. So we do have to be careful of like attributing things to Fibonacci ratio or Fibonacci sequence or the golden ratio if you don't actually have any sort of evidence for that. It is also possible that some things are the golden ratio when in actuality they're just subsequent Fibonacci numbers, which again, okay, they were sort of leaning in that direction, but it's not the golden ratio. It's just, it was an approximation because they used two Fibonacci numbers that were next to each other. The actual Fibonacci sequence is not really Leonardo of Pisa's, i.e. Fibonacci. These things have been around practically forever. It's just that, he was the first one to realize and then start analyzing it and start doing all sorts of cool stuff with it that we now are recognizing. All right. Dialogue between mathematics and visual art has shaped artistic theory and practice for centuries, from classical studies of proportion to modern explorations of abstraction and form. Mathematical concepts such as symmetry, geometry, and numerical ratio have long served as organizing principles for visual space and aesthetic balance. Among these, the Fibonacci sequence holds a distinctive position due to its recursive nature and close connection to the golden ratio, a proportion historically associated with harmony, growth, visual coherence. Fibonacci sequence given by the following. We all know that. Right? Any number that you want to get, you have to add the two numbers before it to get the next one, etc. And this generates the ratio of successive terms that converge to the golden ratio phi, 1 plus the square root of 5 all over 2. This convergence links discrete recursion with continuous proportionality and appears widely in natural systems, including phyllotaxis, branching patterns, biological growth. In theory. But again, evolution is not quite so perfect. And also things tend toward that number, sure, but there's also multiple other numbers that they tend toward because they are the most efficient for a particular shape. If you watch others of the shorts that Professor Hannah Fry put out, she also has a number of videos on again, over-analyzing something and automatically saying like, oh, well, this needs to be attributed to the following because. So again, just beware of over-attributing things to the golden ratio, even if it's not really so much. Such visual regularities have inspired artists to employ Fibonacci-based grids, spirals, and scaling principles as compositional frameworks reflecting both natural order and mathematical structure. Again, Leonardo da Vinci and the Mona Lisa are often like singled out as one of the things that you definitely can attribute to the golden ratio and or to like a Fibonacci spiral of rectangles. And again, not so much, but just be aware. There are others that do have, like they literally started with Fibonacci spirals with the squares and then started working from that. And sure, we can discuss that if it comes up. During the Renaissance, artists and theorists emphasized geometry, proportion, perspective as foundations of visual representation. Although Fibonacci numbers were rarely cited explicitly, proportional systems closely related to the golden ratio informed studies of anatomy, architecture, and pictorial balance. Mathematics thus functioned as an underlying structural guide rather than a decorative element. In the 20th century, Cubism introduced a decisive transformation in the mathematical organization of visual form. By rejecting single-point perspective, Cubist artists fragmented objects into geometric facets and reassembled them through multiple viewpoints. This process may be interpreted mathematically as geometric decomposition and recombination, governed by proportional division, recursive subdivision, and modular organization. While Cubist painters did not explicitly invoke Fibonacci theory, the internal logic of Cubism closely aligns with Fibonacci principles such as repetition with variation, hierarchical scaling, and balanced whole-part relationships. Aim of this paper is to examine how Fibonacci sequence functions as a unifying mathematical framework across representational Cubist and abstract painting. Rather than treating Fibonacci patterns as decorative motifs, we emphasize their structural role in organizing visual space and guiding abstraction. Through mathematical analysis, historical context, and selected artistic case studies, we demonstrate how Fibonacci geometry continues to inform contemporary visual abstraction and mathematically grounded painting. The relationship between mathematics and art has deep historical roots, extending back to classical antiquity and reaching a mature synthesis during Renaissance. Artists and scholars of this period increasingly recognized that numerical proportion, geometric harmony, and spatial order could serve as foundations for visual beauty. Among these mathematical tools, the Fibonacci sequence was introduced to the Western world by Leonardo of Pisa in the 13th century and emerged as a key structure linking natural growth patterns to aesthetic principles. Renaissance artists such as Da Vinci explored proportional systems derived from mathematics, including the golden ratio, which is intimately connected to the Fibonacci sequence. Although Leonardo did not explicitly reference Fibonacci numbers, his studies on anatomical proportion, architectural harmony, and geometric form reveal a philosophical commitment to numerical balance and modular growth that resonates with Fibonacci's recursive structure. This emphasis on hidden order and proportional logic would later reappear in modern art, where classical perspective was deliberately dismantled in favor of structural analysis. In the 20th century, Cubism offered a radical reinterpretation of mathematical structure in art by fragmenting objects into geometrical planes while reassembling them according to internal compositional logic rather than optical realism. While Cubist artists such as Pablo Picasso and Georges Braque did not explicitly employ the Fibonacci sequence, their emphasis on modular decomposition, repetition, and proportional balance parallels the recursive hierarchical principles underlying Fibonacci growth. Again, with the, well, not really, but, you know, pretty close. Or at the very least, you know, they were grasping toward it, whether or not they realized it. These ideas were further abstracted by artists such as Vasily Kandinsky, who explicitly associated form, geometry, and rhythm with mathematical spiritual order. Kandinsky's abstract compositions emphasize dynamic balance, geometric relationships, and structural harmony, aligning closely with Fibonacci-inspired notions of progression and self-similarity. In parallel, artists such as Salvador Dali directly incorporated the golden ratio and Fibonacci-based proportions into the works like The Sacrament of the Last Supper, demonstrating an explicit synthesis of mathematical ratio and artistic intention. This historical trajectory from Renaissance proportion through Cubist structural analysis through Kandinsky's abstraction and deliberate Fibonacci-based compositions provides the foundation for contemporary explorations of the Fibonacci sequence in painting. It illustrates that the dialogue between mathematics and visual arts extends beyond explicit numerical usage, encompassing deeper structural principles that continue to evolve across artistic movements and aesthetic frameworks. The Fibonacci sequence is defined as a series of numbers where each number is the sum of the two preceding. Begins with 0, 1, continues indefinitely 0, 1, 1, 2, 3, 5, 8, 13, etc., etc. Ratio of successive Fibonacci numbers approximates the golden ratio, starts approaching 1 plus the square root of 5 all over 2, yes. Show the closed form, etc., etc. Visual art and geometry. Phi governs spatial balance, placement of elements such that neither dominates the other, creating a dynamic equilibrium that appeals naturally to human perception. Each Fibonacci number can be geometrically represented as a tiling or proportion of space. For example, the Fibonacci spiral is obtained by connecting quarter circles inside squares with side lengths equal to Fibonacci numbers. The resulting spiral approximates a logarithmic spiral expressed in polar coordinates as r equals a e to the b theta, where b is natural log of phi over pi over 2. This curve symbolizes self-similar growth and appears in diverse natural phenomena from sunflower seed arrangements to the shells of nautilus and branching of trees. Not exactly. In the mathematical art, this spiral captures the idea of infinite expansion from finite recursion, bridging algebraic recurrence and geometric beauty. So if you were to measure the actual volume and or linear length and or whatever else of a nautilus shell and all that other stuff, it is not necessarily going to be 1.6. It is going to be all over the place. The you could do this at home, right? So get some sort of precision measuring device. There we go. Like, for instance, the vernier caliper. And if you were to actually measure out each successive joint, the middle, I guess, of each individual joint, to the tips of your fingers, and then compare that particular value. This is, keep in mind, this is only one finger, so let's see how it goes. 5 point. Okay, where am I reading to? Yeah, that thing. It's been a while since I've used these. Can you tell? Uh, 5.2 centimeters. Okay, so 5.2. Oops. 5.2 divided by. And in fact, right? Let's even go one more decimal place if we can. I think there's a thing for that. No, 5.31. I think if we go to the other side, that's even smaller tenths. 5.31 divided by. And then we go to the previous knuckle and do the same. Trying as best I can. To the middle of this knuckle. We get a 2.50. That doesn't make any sense. Hang on. 2.51. Gets us a ratio of 2.1155. So very much not 1.618. If you continue carrying on to try and get this, it is possible that all the averages on your body could end up coming up closer to 1.618. It is also possible that this is all just kind of bunk and meh. Okay, next one is yeah, I must be reading this wrong. 10.0, like 10 divided by 2, no, 5.3. 1.88. So, closer, but again, not really. Like, even if I assumed that I got the other one wrong and kind of like rounded some of the number, rounded the numerator down and then rounded the numerator denominator up to where I think it probably was, should have been like 2.55 instead of 2.51 or something like that. That only gave me a 2.07, so like it's not even close. And like I said, the other one, it's the full length from tip of the finger to back of the main knuckle compared to tip of the finger to middle knuckle on my middle finger is 1.886. So, like I said, these numbers are all over the place. Are they actually the correct values, if you will, in order to get perfect beauty of the human body? No. A lot of this stuff is just kind of apocryphal, and it doesn't really follow. Mathematical sequence connects deeply with multiple branches of mathematics. Number theory. Fibonacci numbers satisfy elegant divisibility and modularity properties. For instance, GCD of f sub m f sub n is equal to f sub GCD of mn, and the sequence modulo k is always periodic, Pisano period. Combinatorics, f sub n counts the number of ways to tile a 1 by n-1 board using 1 by 1 and 1 by 2 tiles. It also enumerates binary strings of length n-1 with no consecutive ones. Linear algebra, the recurrence relation could be expressed as a matrix power. All right, so f sub n plus 1, f sub n is equal to 1110 raised to the n times 10. This form enables spectral analysis. The eigenvalues of the matrix are phi and psi, reaffirming the central role of the golden ratio. Psi, I'm guessing, is probably 1 minus phi, but I don't actually know. We could find the eigenvalues pretty easily. 1110, you say? Okay, so if we are in fact running a eigenvalue for the matrix 1110, and we are augmenting this with 0, 0, and this is going to be on the main diagonal. We get a minus lambda, because again, this was a minus lambda I has to be equal to 0 in order to make this work. Sorry, determinant of that. So we're not augmenting yet. All right, this is going to be lambda times lambda minus 1. If we distribute the negative, minus 1 is equal to 0. This is lambda squared minus lambda minus 1. Right. Good. Lambda equals negative b plus or minus square root b squared is 1 minus 4ac is negative 1 all over 2. Cool. Just to make sure, right? So this is going to be 1 plus or minus the square root of 5 all over 2. Lambda 1 is equal to phi, our golden ratio. Lambda 2 is equal to, in this paper, psi, which is equal to 1 minus phi. Yeah. Okay, cool. Fractals and dynamical systems. Fibonacci recurrence arises naturally in the study of substitution dynamical systems. Consider the Fibonacci substitution. Sigma is A mapping onto AB and B mapping onto A. The associated substitution matrix is the exact same as the transformation matrix in the linear algebra one, and therefore the eigenvalues are phi and psi. Iterating sigma generates infinite words whose letter frequencies converge to the normalized Peron-Frobenius eigenvector of m sigma, giving the limiting ratio phi of a's to b's. Geometrically coding these words by intervals produces the Fibonacci quasi-crystal, a one-dimensional self-similar tiling with inflation factor phi satisfying lambda equals phi lambda union phi lambda plus 1. Functional equation expressing exact self-similarity. The spectral properties of the tiling dynamical system, x, sigma, and t, are governed by m sigma, linking Fibonacci growth to the pure point diffraction spectrum characteristic of quasi-periodic structures such as Penrose tilings. Artistic illustrations from Leonardo to Turner. Mathematical harmony, as embodied by the Fibonacci sequence and golden ratio, has long served as a guiding principle in visual art. The interplay between proportion, symmetry, and visual balance can be vividly observed in the compositions of both Renaissance and Romantic masters. This section highlights how mathematical ideas are manifested in two celebrated examples. I told you it was coming. Leonardo da Vinci's Mona Lisa and J.M.W. Turner's landscape paintings. I mean, everybody thinks they know. Leonardo's Mona Lisa, 1503-1517, housed in the Louvre Museum, is often cited as a paradigm of mathematical beauty in art. Numerous geometrical analyses reveal that spatial organization of the portrait approximates the golden ratio, which is directly related to the Fibonacci sequence. Golden ratio, or golden rectangle, or Fibonacci spiral is superimposed in the... Yeah, this is something that, like, Dr. Hannah Fry is very bothered by. Because, like, you can see here, right, they've got the bottom of the rectangle essentially close-ish to where her elbow is. Then the midline is, I mean, it's not a midline, but, you know, the 1.6 line is on the bottom of her mouth, just above the chin. Why there? Why isn't it at the bottom of the chin entirely? Why isn't it right across the mouth? Why is it in the middle of those two places? And then the next one is underneath her eyes, rather than at the nose or at the eyes themselves or at the actual eyelids, eyelashes, across the pupils, like anything. You got nothing. And, like, yeah, it sort of grazes the top of her head, which makes it look like the top of her head matches the spiral, but you're just superimposing a series of rectangles on top of a painting and being like, haha, it follows it. I'm sorry, by the way. But, like, literally, you too could go onto any art website and superimpose that particular Fibonacci spiral in some orientation on any painting you want, and you will likely come up with a few that get pretty close. When a golden rectangle or Fibonacci spiral is superimposed on the painting, key features such as the head, eye, but they're not. They're not close. They're really not. Each visual segment grows in harmonious ratio to a previous one. Again, not to mention, that's not even the whole painting. Or that's too much of the painting. Facial region and torso. Torso. Your torso ends here. Your torso ends at your hips. You can't see hips. Oi. Though there is no definitive historical evidence that Leonardo consciously applied the golden ratio formula, his deep study of geometry, anatomy, and proportion recorded in the Codex Atlanticus suggests a strong awareness of mathematical harmony. Fibonacci-based spiral division in Mona Lisa reflects an organic equilibrium, visual metaphor for self-similar growth, and the recursive perfection of natural forms. J.M.W. Turner and the Geometry of Light. Joseph Millard William Turner, 1775 to 1851, one of Britain's most visionary romantic painters, integrated mathematics, geometry, and scientific observation into his practice. Appointed professor of perspective at the Royal Royal Academy, Turner explored geometric projection, vanishing points, and atmospheric optics with mathematical precision. His sketchbooks contain constructions of spirals, circles, spirals, linear diagrams used to guide the composition of his luminous seascapes and skies. Two particular works exemplify this union of art and mathematics. Norham Castle Sunrise, 1845. Turner structured the composition through linear perspective and horizon geometry. Placement of the castle and reflection along the horizontal phi divisions of the canvas create a visual equilibrium analogous to the golden ratio. I would love for you to tell me where those are. Please. Gradation of color intensity across the sky can be interpreted as a continuous exponential decay, which is mathematically expressed as I of x equals I sub 0 e to the negative kx, representing light diffusion. Bring it, famished. Tell me where the phi is in this particular painting. Gradation of color intensity across the sky can be interpreted as continuous exponential decay. I don't agree. ADHD is too much for your psychology at the moment. In two ways. Well, you are now here to listen to me piss and moan about why this is wrong. You're stuck now. Yeah, this word approximately is doing a lot of heavy lifting here. I can't agree with this. In fact, right? Let's see if we can. I cannot. Interesting. Right. I can't take that. I am going to go over to GIMP. And pull this in. Okay, we are going to, okay, good. So I can copy this. Oop, nope, don't select all. No. Really? Ugh. I can't just take it. Fine. We'll come out just a little bit beyond the painting. Copy and paste. Okay, so let's figure out what this is doing. So you all, window capture is going to switch over to GIMP. Okay, and then we are going to control zoom. And, all right, who knows how to use GIMP? I want to select all pure white and remove it from the canvas. I know that's possible. Select all. Like, I want it to crop, but I want it to crop automatically. I don't suppose that's actually possible. I mean, it is possible. But... Okay. Good. Cool. Now select all? No. Okay. Fit canvas to selection. Okay. I want this to crop the entire crop to content. Question mark? No, already did. Fit canvas to selection. Apparently already did. Nope. Don't fit canvas to layers. That gives me the white yet again. Canvas size, center. Okay, let's just suggest that this is actually correct. If not, you know what, it's close enough. 446. 446 divided by parentheses 1 plus square root of 5 over 2 is going to get me multiplied by 2 with the entire thing, which gets us to 275. Now, where is 275? That puts us right here. So, okay. I have to say, not terrible. It does cut the animal into there, and reasonably so. It puts the animal front leg on one side, hind legs on the other. I assume that's a dog. However, what I would have assumed was that this line in the portrait would have been selected for. So it was going to be this value rather, right? Because here we have this edge of the grass stuff, or like some feature on the castle, which would have been selected, not just the dog, and only the dog. Because that's what's going on here, is that where the authors of this paper suggested this is going to be pretty much right there with the dog and literally nothing else. If we go to the other side, then what exactly are we lining this up with? There's nothing here. There's literally nothing here. All right, what does he actually say? They. What do they actually say? There's more than one. The placement of the castle and reflection along horizontal feed divisions of the canvas. Horizontal feed divisions. Okay, so I'm going the wrong way anyway. 329. 329. 203. Okay, so from 0, we go 200. Oops. Man. Ugh. Okay, from the top. 0, 0, right? We go to 200, 203. Okay, so reasonable, I suppose, to assume that this is the reflection line between the actual castle and its reflection. Pretty close. I'm fairly well convinced that the actual reflection is here, which is 127, rather than, no, oh, that's where my cursor is. Ugh. Tricks. Right? This is 203. Ugh. No. Nope. Damn it. All right, 0, 0. All the way to the edge, 203. Okay, then we take this and we put it to the bottom. Okay. Again, there is the one reflection which might be approximately 1/5 the way through all of this, but then when he goes to the other horizontal phi divisions of the canvas, the other horizontal phi division of the canvas goes through the sun, presumably, it's kind of nebulous, and doesn't interact with the castle at all. So I am not seeing this at all. So again, this way, maybe. We could maybe see this as a reflection of the castle. You know, this being our reflection line, or our horizon. Right? Again, I think it's probably a few pixels lower, but I'm not going to pick too much at that, because that's a matter of like perspective at this point. Okay. Gradation of color intensity across the sky can be interpreted as continuous exponential decay. I don't know how to measure that. How can we... color... No, there's a way to do this. I mean, gradient, I guess, but... like from here to here. Right? If we wanted X... I can't really do that. But anyway, break is happening. So be back in a few minutes. I'm not sure I'm going anywhere. I'm going to just rant. Old man yells at clouds. See you in 3. Hey YouTube, how you doing? I don't know how to get a color gradient measured. I mean, it's not even a color gradient. It's it's measuring gradient. That's not what I wanted. Via a mathematical formula. What word did he use? Spectrometer, maybe. How do you determine color intensity? Oh, I don't like that. Gross. Change the intensity range in a channel. All right. Levels. Change color, brightness, contrast, transparency in a sophisticated way. Curves. Reduce the number of colors. Posterize. Convert all colors to corresponding shades of gray. Desaturate. Okay. Eh. All right, well, I'm not going to find it, so discard changes. It's fine. We're not really doing anything here. Right. So now you can all see me absolutely get mad at things. Frosty Morning, 1813. This work demonstrates precise control of vanishing lines, leading the viewer's eyes toward a focal point in the distance. Spatial contraction obeys the principle of geometric projection. All parallel lines meet at infinity. Elegant manifestation of projective geometry in art. Turner's Frosty Morning reveals a tightly organized geometric structure shaped by the golden ratio divisions, logarithmic spirals, classical compositional grids, vertical and horizontal partitions at x equals w over phi and y equals h over phi align closely with major narrative elements, particularly horses, cart, and luminous horizon, thus dividing the landscape harmonically into balanced regions. Sequence of nested golden rectangles with widths w over phi squared, encloses progressively finer visual features, forming a recursive phi-scaled hierarchy that echoes the painting's rhythmic spatial flow, superimposing an approximate Fibonacci logarithmic spiral generated by quarter circle arcs, satisfying that traces a natural viewing trajectory with the foreground through a central horse and cart to the distant atmospheric light. Canvas diagonals intersect near the horse, cart, wheel, and right-hand worker, reinforcing the compositional center, while the rule of thirds grid corresponds with placements of tree, line, family group, and labor. 1/3 is not the golden ratio, in case you were curious. 1 over 1.618 is approximately 0.61 or 0.62. So, yeah, if you squint really hard, again, you might be like, well, 0.66 is pretty close to 1.618 or 0.618. Golden ratio lines, spiral curves, diagonals, and third divisions concentrate visual attention around key focal points, revealing a compact yet powerful mathematical framework underlying Turner's atmospheric landscape. Okay, so yet again, this is almost exactly rule of thirds here. Like, the horizon is at the first third along the white line at like near the bottom here. There are other elements that peak up to, roughly speaking, the red line, but they are not like to the red line and stopping. They are not just beyond the red line. They are like kind of all over the place compared to the red line, almost as though the red line didn't even matter. And then if we look at the yellow line, like, sure, it's going through the cart, I guess. The lady here being at the other one is kind of interesting, so I will possibly give them that. But then, like, all this other stuff over here, like, there's not much going on. Like, I guess the one tree in the corner, but like this might be based on a real location. So I'm not sure how you're going to justify, like, oh, hey, why aren't those on the other side? In fact, right, if we went to the other side, this yellow line more closely aligns with these people over here. This yellow line corresponds pretty roughly with this pothole over here. Oh boy. And then the next yellow line is like right down the middle of the road. So that, that has just as much credence, if not more so, than this random place over here that has absolutely nothing attached to it. And then in the corners, yeah, sure, why not? There's not really much else over here. Arrangement of horizon, road, and architectural forms exhibits proportional divisions close to the golden ratio, establishing balanced visual geometry. Moreover, distribution of luminance, moving from bright mist-filled morning foreground to the muted atmospheric. That's just literally how sight works in a foggy place like England. Follows an approximate exponential decay. Together, these structural features reveal the mathematical organization underpinning Turner's treatment of atmospheric depth and early morning illumination. Again, that's just how vision works. Like somebody who has a decent ability to see things can just do that. Just be like, okay, well, it looks like this, and so I don't need to worry about what the precise mathematical formula is for this. We're just going to mute things as they get further and further away. Oh, look, I have my, visual cues literally in front of me, and I can see how to mix this to make it better. So I don't see this as proof positive. This is one of those, I think, squint hard and you can maybe see it. Through these works, Turner bridges science and art, demonstrating that the play of light, space, and form can be grounded in quantitative principles. Is anything in his journals suggesting this? That he actually went in and said, yeah, I'm doing this specifically to match up with mathematics. I'm curious how a late 1700s, early 1800s painter is trying to set up an exponential decay profile for his paints. Literally, did he Use of perspective, luminance aligns, exponential decay. Thus, Leonardo's proportional geometry to Turner's spectral perspective. Mathematics provides both invisible architecture and philosophical foundation of art. In the language of Fibonacci growth and geometric harmony, these masterpieces remind us that beauty often arises where mathematical order and creative intuition intersect. Again, I think that he just had a good eye for art. And maybe he used some mathematical formulae to do stuff, but not to figure out the depth of field as far as how far back can we see. I don't believe it. Not without further evidence. Vasily Kandinsky, often regarded as a pioneer of abstract art, developed a visual language grounded in mathematical structure. In his treatise Point and Line to Plane, Kandinsky formalized painting as a geometric system. Point is zero-dimensional nucleus. A line is the trajectory of a point under motion, and a plane is the field in which these elements interact. This framework mirrors fundamental concepts in geometry and dynamical systems, where motion generates higher dimensional objects. Kandinsky's compositions frequently employ symmetries, rotations, and affine transformations, creating visual analogs of linear operators acting on geometric primitives. His recursive use of circles, triangles, and arcs produces quasi-fractal layering, reinforcing the structural logic seen in Fibonacci spirals and self-similar growth. Thus, Kandinsky's work forms a bridge between abstract painting and mathematical thinking, revealing an aesthetic grounded in geometry, proportion, and the algebra of visual forms. Yeah, like modern day, right? You could do it in the modern day and like calculate out exactly how much of each pigment you would need to make the precise shade that you needed to get, a foggy morning. But like in the 1800s, I guess, maybe? I don't think it's going to work. Piet Mondrian's perfect balance. Okay, well, we're going to have to look that one up. Oh, yeah. Found 1 artworks, National Galleries. But yeah, the they cut you off on that one, man. Broadway Boogie Woogie apparently is an interesting one if you look up his. That's exactly what I typed in, you jerks. Oh, no Oxford comma in the URL. Touche. But there is an Oxford comma in the name of it under the description. Man. Yep. Well, that makes it interesting anyway. Okay, so like Kandinsky, right? That's very abstract and all sorts of crazy stuff. So can we even can we even come up with literally anything in this stuff? Represent two distinct yet mathematically related phases of abstraction. Composition 7 exhibits continuous, fluid, and highly nonlinear motion fields. Composition 8 is governed by rigid geometric primitives such as circles, triangles, and lines, arranged according to an underlying operator system. That's a bold claim. Both works may be interpreted in Hilbert space, H equals L squared omega of omega in R3, where each visual element is generated by the action of geometric operators on a finite set of basis shapes. You're going to have to convince me of that one. 7 as a nonlinear dynamical flow. Sweeping arcs, curves, and color gradients can be modeled as the evolution of an initial... Is this just because they were on the publisher-perish system? They had to come up with something. Like, maybe an artist could, again, squint hard and see that, yeah, of course they're absolutely right. But, like, I'm very suspicious. Sweeping arcs, curves, and color gradients of composition 7 can be modeled as the evolution of an initial geometric field, phi0, under a nonlinear flow. Phi of t is equal to big phi of t of... or no. Where big phi sub t is a semigroup of diffeomorphic transformations representing sketching, shearing, and curvilinear advection on omega. These operators are analogous to those arising in fluid dynamics and nonlinear PDEs, generating continuous deformations rather than discrete geometric orbits. Painting's dense layering corresponds with superpositions at different times, so composition 7 may be viewed as a time-integrated field of nonlinear operator actions. You mean like painting? Producing the visual analog of a dynamical system with high-dimensional trajectories. Composition 8 as an affine operator system. Kandinsky's operation 8. Stuckey still here? May be interpreted as the realization of an operator system acting on a finite set of geometric generators. Let omega in R squared be the canvas and consider the Hilbert space where the three components represent RGB color channels. Fix a small collection of prototype shapes such as disks, line segments, triangles, and polygons, each given by the indicator of a region multiplied by constant color vector. Let G be the semigroup generated by translations T sub A, rotations R sub theta, and anisotropic scalings S sub lambda on omega. Each element U in G acts unitarily up to scaling on H via UF of X is equal to F of U inverse X. Visual constant of composition 8 can be modeled as finite superposition. C sub k in R3 encodes color intensity RGB, and U sub k in G encodes the spatial placement, orientation, and size of each element. Orbit set forms a structured frame for span of phi sub j, so that geometric redundancy and overlap yield a stable representation of the composition. Kandinsky's interplay of circles, radiating lines, and intersecting polygons corresponds in this model to the interaction of commuting and non-commuting operators in G, producing visual analogs of spectral decomposition. concentric circles as eigenmodes, and interference, crossing the lines as superposed directions. Thus, composition 8 may be viewed as an explicit example in which the abstract operator system on geometric basis H generates a complex yet mathematically controlled field of visual forms. I don't think I believe them. Now, maybe I'm just not smart enough in terms of the actual math and in terms of what they're trying to say about art. But, yeah, I can't say I believe them. And maybe that's also me being biased against this. Because again, it started out bad and it went way poorer. Again, Hannah Fry just did like a huge rant about this on YouTube Shorts. So I recommend checking that out. She's brilliant. And yeah, like the end points of your rectangles are going to matter if you're going to claim that like all of this stuff fits the golden ratio. Like, cool. I don't really believe you. So here it says the torso, but your torso ends at your hips. So that's like at the bottom of the frame. And this conveniently is just placed above her left elbow instead of like at the part where her shirt is. Or why is it across the middle of her right wrist? Is that really what you're aiming for? Like, what are we doing? I don't know. I don't like this one at all. I'm gonna skip. Move on. We getting toward the time where I go to bed, maybe. And I think we will go and check out Ivan. Ivan Neo is on and doing science and philosophy as usual. So we're going to head over there. I will be back tomorrow to probably figure out what game to play next. Oh no. We're doing blueprints. Right. So tomorrow's blueprints night. We're going to try to figure out more stuff and see what other puzzles we have available. I've got my notes going. I have to go to a treasury meeting in the morning for scouts. So we'll see if I can get all my bank balances in order. I mean, they're in order. The question is whether or not I have them like printed out and stuff. Have everything, all the spreadsheets 100%, or if they're like 90%. So, hope you all have a good night. I'll see you later. My name's Obi-Wan Pez. This is N Simplex Pachinko. We will be back on Wednesday for more mathy type stuff. Thursday, we have been doing a like RPG prep for Titan's Grave, and Friday we do other games. So we'll see how we go with that. And then as of Friday, we get our keys to the new place. And as of next Monday, I'm probably not going to be doing streaming because it's just moving everything over there. So We'll figure it out. And then I'm going on vacation like the next week after that. It's fine. Everything's fine. We'll see you all later. Have fun.